Greetings, everybody. Learning is a hobby here with your problem of the day. I do apologize for posting this a little bit late, but I didn't have a chance to record this video last night to post it for the morning just because time got away from me. But I do have it for you here, and I hope you enjoy it. So let me bring up the problem and I'll explain. Or actually, before I even bring up the problem, let me do this. Uh, Some of you, I think, probably are familiar with elementary calculus. Some of you probably may not be. When I was a student, an undergraduate student, and I took calculus for the first time, freshman level calculus, they show you the logarithmic, sorry, the integral definition of the natural logarithm, and it seems like it, at least from in my experience, it came out of nowhere. Like there was no motivation given for it. Maybe some of your teachers did give motivation for it, but they just sort of plop it in your lap and then they show you that it works and then you use it. But I wanted to know where it came from because it looks so strange. When they showed me the definition, I was like, how did people come up with that? It looks so weird. Why would anyone define the logarithm that way? And how does it relate to, like, exponents and stuff, which is the way you're taught to think about logarithms in your algebra course. So that's what I want to do for you guys here. I want to give you the motivation for the logarithm, the integral definition of the logarithm. And let me just say, when I was an undergraduate student, like I said, they gave us the definition, but they never explained where it came from. So, it's in my nature to want to know where things come from. So I went on a journey looking for, where did this formula come from? And the place where I found the motivation was in Tom Apostol's famous book Calculus in two volumes. This formula is in volume one, um, and or the motivation that I'm going to show you here is in volume one. Um, there's two volumes. Volume one is single variable calculus mostly, and volume two is multivariable calculus mostly. There are other topics interspersed in there as well, but mainly those are the topics in volume one and volume two. Um, Apostol's book is fantastic. It contains like a bunch of really great jewels that you don't often see in other more standard texts in calculus, like Stewart's Calculus, which is a great textbook. I have nothing against Stewart's Calculus. But if you are interested in mathematics and want to dive a little bit deeper into things, I think Apostol is a fantastic read. When I first discovered it, I was, it was like a magical tome to me, and I just couldn't stop. I got obsessed with it, and I had to read the whole thing. Um, I think Spivak's book is kind of like that too. So if you're not familiar with Apostol's book, and you're interested in math, I would say check it out. It isn't an easy read, but it's worth the effort. The other One of my pet peeves, though, is that if you try to find the book new, it's really expensive, which is kind of a shame because I feel like it would be nice if this book were accessible to a larger audience of people. But anyway, let me get off my soapbox and I'll get to the problem for today. Okay, so where are we? Here is the problem of the day. Just want to move this out of the way. Okay. Where does the integral definition for the natural logarithm come from and why is it natural? So if you haven't taken calculus, this is the formula that I'm talking about. We define the natural logarithm of x to be the integral from 1 to x of 1 over t dt. So you can see that this might be a little bit weird, particularly because of the way you think about logarithms in algebra, which is in terms of exponents. And there's no exponents that show up here at all, right? So I just want to motivate where this came from. So one of the most important properties of logarithms, I would say the most important property of logarithms, is that they turn multiplication into addition. Um, in fact, when they were invented by John Napier in the 15th or 16th century, I actually forget which one. You can let me know down below. And the motivation that I'm going to give you here is not the way that Napier derived the logarithm. Um, this is a more modern way of doing it. But it was invented to make calculation a little bit easier. Back then, they didn't have computers, obviously, they didn't have calculators, so people had to do things by hand. They did have tables, books of tables of calculations and so on, but those could be um, kind of unwieldy. They did have tables for logarithms here too, but what logarithms let you do is that it lets you turn the harder operation of multiplication into addition. Anyway, this is not a course on logarithms. I tend to fall into teacher mode when I'm doing these videos, and I got to be careful about that. So consider this functional equation. F of x y equals f of x plus f of y. We would like the logarithm to have this property. So let's look at the functions that satisfy this functional equation. There's a trivial solution. For example, what if f is constant? So say f of x is the constant c for all x, y, and r. Then c equals f of x, y equals f of x plus f of y, which is 2c, which implies c equals 0. All you have to do is, subtract c from both sides, and you see that c is 0. Therefore, the only constant solution to the functional equation is f of x equals 0 for all x and r. Okay, so we're interested in a non-constant solution. So what about a non-constant solution? Is there one? What are the properties of what would be some of the properties of a non-constant solution? For example, is 0 in the domain of f if f is a non-constant solution to that functional equation? Well, let's see. F of 0 is f of 0 times x, which is f of 0 plus f of x, which implies that f of x equals 0 for all x and r. So unless f is constant, 0 can't be in the domain of f, because if 0 is in the domain of f, then the function is constant. All right, what about plus or minus 1? Those are some important numbers we should probably know the value at if the function is defined there. F of 1 is f of 1 times 1 equals f of 1 plus f of 1, which is 2f of 1, which implies that f of 1 is 0, right? Again, you just subtract f of 1 from both sides. Excuse me. And also, we want to know what the value of f of negative 1 is. So 0 equals f of 1 equals f of negative 1 times negative 1, which is equal to f of negative 1 plus f of negative 1, which is 2f of negative 1, which implies, again, that f of negative 1 is 0. Next question, does f have any symmetry? Let's look at f of negative x and see what happens. F of negative x is f of negative 1 times x, which is f of negative 1 plus f of x equals f of x, because f of negative 1 is 0, which implies that f is even, so that if the function is non-constant, it has even symmetry. So does the constant one, by the way, but we'd like to know for the non-constant one as well. Okay, what if f is differentiable? Um, so we would want ideally the logarithm to be a differentiable function as well. Let y be fixed. Then if we differentiate both sides of the functional equation, we get that y times f prime of xy is the derivative of f of xy by the chain rule. And on the right hand side, we get f prime of x, because the derivative of f of x plus f of y would be f prime of x plus the derivative of a constant. And if you remember, the derivative of a constant is always 0. All right, if x equals 1, then y times f prime of y equals f prime of 1, which implies that f prime of y is f prime of 1 over y for all y not 0. And notice, if f prime of y is equal to f prime of 1 over y, then it's monotonic, right? Because f prime of y is a constant. So whatever the value of y is other than 0, right? If y is positive, then the derivative always has the same sign. Same thing if y is negative. Notice that f prime of y is monotone, so it's integrable then by the fundamental theorem of calculus, which, if you're not familiar with the fundamental theorem of calculus, unfortunately, I'm not going to go into it here because, again, I want to keep these videos short, but you could look it up. F of x minus f of c is equal to the integral from c to x, f prime of y dy, which is the integral c to x, f prime of 1 over y dy. And then I just changed factor out the f prime of 1, which you can always do for an integral. And I changed the variable to t just so it matches with the definition that I had at the top of the page. And if c equals 1, then plugging 1 in for c up above, we get f of x equals f of x minus f of 1. But remember, f of 1 is 0, so that's why it's equal to f of x equals f prime of 1 integral 1 to x 1 over t dt. And f of negative x equals f of x implies that f of x is f prime of 1 times the integral 1 to absolute value of x 1 over t dt. It has that even symmetry, right? And notice that if f prime of 1 is 0, then f of x is constantly is the constant function, equals 0. So we can assume that f prime of 1 is not 0. Then we can define a new function g of x equal f of x over f prime of 1. And notice that that's equal to this integral, and we're almost there. This is the integral from 1 to absolute value x, 1 over t dt. Notice that for any constant c, if f is a solution to the functional equation, then so is g sub c of x, which I'll define as c times the function g of x. And you could see why it satisfies it here. I won't go through this in detail, but you get the idea. It satisfies the functional equation for any value of c. Lastly, we would like g sub c to be a one-to-one function because we know from algebra that we want logarithms to be one-to-one. We can take domain g sub c equal to the set of all real numbers x such that x is positive, and then we get the integral g sub c of x equals c times integral 1 to x 1 over t dt. And that's our candidate for log base c of x. If f prime of 1 equals c equals 1, then we would have L of x equals the integral from 1 to x, 1 over t dt, which will be our basis for defining logarithms of all bases by simply multiplying L of x by a suitable constant. In fact, what you do if you want the log base c, you divide the integral by 1 over L of c. So it can be shown that L of x satisfies the functional equation and all other properties we would like logarithms to have. I'm not going to do that here, obviously, but that's usually where all calculus textbooks go. They'll give you the definition and they show you that it satisfies all the properties that you want. We can also show that the number e, which if you remember from algebra is that special base, it's the base of the natural logarithm, which is approximately 2.718, et cetera, is such that 1 equals the integral from 1 to e 1 over t dt. Lastly, we can show that log base c of x equals 1 over L of c integral 1 to x 1 over t dt, which is why L of x is called the natural logarithm. And any logarithm can be defined in terms of it. So that's why it's natural. So I hope this video wasn't too long. I hope you guys found it interesting. As always, let me know what you think down below, and I'll have another interesting problem for you guys tomorrow. I'll see you then.